Alright, hello, my name is Margeat, and I'm serving as a coordinator for the French PoLS community. So on this slide, I put you some of the labs that are really involved into the core of the French PoLS network, but there are others that are part of it. We call it associated labs. So if in any case you are interested into exchanges with this lab or other lab in the community in France, don't hesitate to contact me. We can discuss things. So today we're going to give you a flavor of the work that has been done and that is currently done in some of our institutes. We're going to have 5 short talks, mainly from group from Montpellier and as well from the Institut Curie in Paris. So I will start, and I will tell you today about the feature of this very intriguing molecular machine, the transcription termination factor rho. So, as you all know, transcription is a process of RNA synthesis mediated by the RNA polymerase. And in bacteria, transcription is coupled to translation by the ribosome that is trailing behind the RNA polymerase. At some point, the transcription process needs to stop. This is called transcription termination, and my lab has been studying this process for many years using mainly single molecule methods. And in E. coli, 50% of transcription termination events approximately involve the participation of an external factor called rho. And rho, it's an hexamer protein that will bind to the luminescent RNA at the site of the root site, and it will use the energy derived from ATP hydrolysis to translocate along single-strand RNA, and then through a mechanism that is not well defined, dissociate the RNA to polymerase, so transcription will stop. So on top of doing this job, rho has been shown to be controlling the expression of non-coding small RNA, preventing the formation of R loops, which are DNA RNA loops, and silence foreign RNA in bacteria. And moreover, it's considered to be a good antibiotic target because there is no equivalent, rho has no equivalent in eukaryotic cells, and of course it's a very important factor for the survival of bacteria. So thanks to the effort of the lab of Jim Berger in Berkeley, we know a lot about the structure of the rho hexamer. So here I've represented this hexamer, and rho contains 2 RNA binding sites. You have the primary, the PDS, the primary binding site that is distributed around the hexamer here, and then within the whole of the hexamer, you have the secondary binding site in yellow. And this is where the mechanical work will take place. So there is this old model of what the path of the RNA might be around the rho hexamer. So you see the RNA here in black that is going around the primary binding site and then entering the hole to go through the hole where the work is going to take place. So the activation of rho is a multi-step process. You have rho binding to this root site, and then you have several steps of rho RNA contacts that are made, and at some point the hexamer will close, the protein will be activated, and then ATP hydrolysis will start, and translocation will start. So we know that rho is able to bind to single-stranded DNA and single-stranded RNA. However, we only translocate strictly on single-stranded RNA. And we have the RNA-DNA helicase activity, so it can dissociate nucleic acid, but it can also dissociate proteins that are bound to the RNA, even streptavidin, for example, and of course RNA polymerase. So thanks to the structural studies, a model has been proposed for the translocation of rho, which is called the X-Corp model. And so in the crystal structure, the nucleotide bind at the interface between monomer, and each of the monomer is in a slightly different conformation. And each of the ATP binding pockets are in this slightly different conformation as well. So the model for translocation, called the X-Corp model, implies that you're going to have hydrolysis here of the ATP is going to become ATP. The ATP is going to leave, and a new ATP molecule will enter here, and this process will be repeated around the hexamer sequentially. And each time you have this ATP hydrolysis, each of the slight conformational change at the ATP pocket will trigger a slight conformational change of the protein and a change in the contact between the RNA and the protein. So altogether, there is this model that proposes that RNA basically is escorted from the bottom here to the top by contact between the protein and the RNA, and this slight conformational change is what drives the RNA through the hole. And so this is just a model that was proposed by Jim Berger, but this has been confirmed by Arleton simulation by the group of Klaus Schulte very recently. So the question we ask in this system are two. There are many, but the one I'm going to address today are: what is the fate of the contact between the primary binding site and the RNA after translocation has started? So I will explain to you this and show you how we have solved this problem in single molecular manipulation. And then, is this simple escort model that I just presented sufficient to explain some biochemical data on row translocation and RNA contact? And for that, we're going to use combinatorial biochemistry. So there are two main models, actually three, but we can stick to these two, for row translocation and the outcome of the row RNA contact. The root-free model postulates that after translocation has started, row will lose its contact between the primary binding site and the RNA. So all of the yellow contact here is going to be lost, and row will just move like on a string towards the RNA polymerase. So you have the loss of this contact. The second model is called theta tracking and postulates that row is going to maintain this contact during translocation. So it's going to sit there on this high affinity site, and it's going to translocate the RNA, and the outcome of this model is that it's going to create a loop of RNA while you are translocating. So in order to distinguish between these two translocation models, we have used magnetic tweezer in a very simple way, not the fancy way we have seen this morning. We use magnetic tweezer just to look at the change in extension of the tetra. So we have a single-stranded RNA that is partially hybridized to a DNA strand and immobilized between a surface and a magnetic bead. We're going to apply some force, and what will happen is that when row will bind and start translocating onto this construct, if it's making an RNA loop, we expect the extension of the construct to decrease. If it doesn't make a loop, the extension shouldn't change. When we do this experiment, we observe consistent decrease in RNA extension only in the presence of ATP on around 25% of our bits, and we never see this decrease in the absence of ATP. So we have this ATP-dependent shortening of the RNA, and from this type of curve, we can define first the rate of the translocation of row is going to be the slope of this decrease, and then we can define the positivity, which is the extent of this decrease. This is how long row is able to travel before releasing the RNA. So from this data, we can construct histogram and determine the velocity of row, and we have found a mean velocity of around 56 nucleotides per second, and its positivity around 50 nucleotides. And these two values are consistent with the model, which is sort of kinetic competition with RNA-P, which postulates that row needs to be able to travel on RNA faster than RNA polymerase to be able to catch up with it and then dissociate it. And the positivity is consistent as well, but with the distance that is generally found between the binding site of row and the termination site. I'm going to switch now to the second part of my talk, which has to do with this escort model and some intriguing observation we had using combinatorial biochemistry. So the escort model postulates that row translocation should occur in one base mechanical step, right? Simple And on each hydrolysis step, the RNA should move by one base only. Several groups in the world have tried to directly observe this translocation, but so far nobody succeeded using optical tweezer, magnetic tweezer, single molecule thread. We have tried with thread ourselves, but we never managed to have convincing data. So there is no direct validation of this model. What this model postulates as well is that each RNA base is equivalent to the next. Basically, since it's a simple export model, on each step, the RNA should be equivalent to the first one, to the one before or the one after. So in order to test this, we have tried to mutate each RNA base and see what is the effect of this mutation on the raw reaction. So I told you before that raw is only able to translocate on RNA, not on DNA. So the only difference between DNA and RNA is here the 2' OH group that is present on RNA, but not on DNA. So what we have done is that we have systematically removed this 2' OH group on an RNA chain and look at what is going on raw activity. So to do so, we have used a combinatorial approach, and this has been done by our collaborator Margeat, called nucleotide analog interference mapping. So the principle is the following. Using in vitro transcription, you randomly introduce in a set of RNA transcript modified nucleotides. So this nucleotide has two modifications. They have a thiol in the alpha position, and they have the 2' OH that has been replaced just by a hydrogen atom. So you end up with this set of modified transcript, and then you're going to make a selection on this transcript. So our selection is just based on raw helicase activity. So you take all this transcript, you run an helicase experiment with raw, you have raw and ATP, and then you end up with two pools. A pool of transcripts that didn't react here, and a pool that has reacted. You separate these two pools, and then using iodine you can cut at the position of the modification of the pool, and then you run the sequencing gel. What is going on is that if the mutation that you have introduced changes anything to the activity of raw, you're going to see a difference on the gel. So for example, here, you have, at this position, you have a band that has disappeared in a reactive pool, which means that if you remove the 2' OH at this position, raw is not able to unwind the RNA-DNA hybrid anymore. So these are real data, for example, and you can see that in some position you have changes between the unreactive and the reactive pool. Most of the time you have the band that has decreases, but sometimes it also increases. It sometimes helps. So once you have all this data, you can report this interference, as we call them, on the RNA sequence. So for example, here you have RNA sequence, and each of the dots is a position where you have an interference. We have repeated this for many constructs, and to our surprise, what we see is that not all positions are equivalent. In fact, we see positions of interference that show a very strong periodicity. And if we quantify this, we have a 6 to 7 base periodicity that you see very clearly here. And using an advanced version of this method, we have been able to show that this loss of activity comes from a loss of processivity of raw. It's not the speed of the reaction that is reduced, it's really raw that falls off when he encounters this mutation. So how can you have this data compatible with the export model? So in the beginning we were very puzzled. We had this first data in 2009, and we proposed that maybe it's not an export model at all. The structure was not available at the time. We are saying maybe raw is taking 7 base steps at the time. But now we would like to propose a new model. So this is an export model. We like to propose a new model taking into the fact that raw is able to translocate using tether tracking, just as I showed you before. Because translocation with tether tracking implies the conservation of these contacts here, and thus it introduces an asymmetry in a raw ring. The export model postulates that the ring is completely symmetric, but in fact, you have an asymmetry here. And actually what happens is that one of the interface is weaker than the other one because the RNA acts as a belt and makes the interface between the monomer stronger, except for one position. So what our model, our new model says now is that when Rho initiates during initiation, the RNA enters the ring, and then Rho enters its catalytic site. And one of the interfaces, we know that one of the interfaces is weaker than the other one. This is the exchange interface. And it's only every 6 nucleotides that this weak interface will correspond to the interface that is not baked by the RNA that goes around. So every 6 bases, basically, Rho will enter this we call regulatory state, and potentially it can exit the translocation cycle and then get inactivated because the RNA will be able to escape. So this translocation by cellular tracking has several implications in terms of biology. We think that it might increase Rho processivity because basically on all 5 other interfaces, the fact that you have the RNA that is still there strengthens the interaction of the hexamer. And it also can allow Rho to generate force at the distance on an RNA. Since Rho is able to shorten the RNA, in fact, it's able to pull on the RNA, and it might be able to dissociate the RNA from the RNA polymerase without even touching it, just by acting at a distance. So, of course, these are models that we would like to test, and these are the new direction now of our research. We are trying to do experiments in the context of the RNA polymerase using nanomanipulation. We also do in vivo experiments in living bacteria to look at the interaction between Rho and the RNA polymerase within the context of bacteria. And also we are now working on other Rho and other RNA from other species, such as Mycobacterium tuberculosis, because M-tube Rho has different features than E. coli Rho, some very interesting characters, and so, and of course it's a great theoretical topic. So we are switching some of our project to Mycobacterium tuberculosis. So with this, I would like to thank the people who did this work. So Veronica Gotcheva was a PhD student, and Antoine Legal, a postdoc in our group. Actually, these 2 people were shared between my group and the group of Marcel Norman in the institute. We specialize in nanomanipulation. And all this work has been done thanks to a very nice collaboration with Marc Villain, who has set up this nucleic acid interference mapping technologies. And thank you for attention.
Thanks for the talk. I have a question about the hydrolysis cycle in Rho. So the picture that you presented in both models is very deterministic in the order in which the cycle happens. Is this actually, let's say hydrolysis happens in one site, how certain can you be that it will be exactly the next site next to it, or there is some randomness in the order?
Yeah, there is no, this model has not been proven, it's just based on the crystal structure, but if you look at the crystal structure, you really see that each of the monomer and the monomeric interface seems to be in a incremental step, I would say, towards the total reaction. So you really have an exchange interface where the nucleotide is there, but it's ready to go. It has a very high P factor, for example. Then you have the ATP, and then you have the ATP, and one of them are in a transition state, if you want, while the other one untouched. So there is quite a good evidence on crystallography that you have this sequential reaction.
Can I ask you, let's call the model as a point model is built-in symmetry, which was broken in your model by invoking a regulatory state. Well, how is that chosen? I mean, there's a choice to be made as to which one is the regulatory state. Where is the symmetry going on?
Yeah, so in our case, actually, it's imposed by the fact that the selection that we made is based on a helicase activity. So you have the single-strand RNA, and then you have the DNA construct. And we see that the first interference peak is always aligned with the beginning of the helicase construct. So we think that this is what imposes the fact that we see this asymmetry.
Well, thanks very much.